So when we say the word circulation, what we're talking about is the line integral of a vector field along a closed path. And closed just means that it has the same starting point as it has ending point, right? So I start in a place and I wander around and I end up in the same place where I started. So, for example, this circle here traversed in a clockwise fashion, that's a closed curve. We don't know what is the starting point and ending point. It actually doesn't matter which is the starting point or the ending point. It only matters what the closed curve is. And so the circulation is defined to be the path integral along a closed path. Sometimes I call it a loop integral for that reason. And because it's called a loop integral, sometimes we use a integral sign with a little circle drawn on top of it to reinforce the fact that this is actually the integral over a closed loop, right? It's not an open path, but the endpoint and the starting point are the same as one another. And so circulation, in a way, is kind of measuring a vector field's tendency to rotate in a manner that's consistent with the orientation of the curve. So for example, I have here a circle that's being parameterized in a clockwise fashion. And also, when I look at my vector field seems to be also circulating in a clockwise fashion. So the way that my vector field is rotating, circulating, and the way that I'm moving along this path look like they're aligned with one another. So that the circulation, I would expect, the path integral along this path, it looks like I'm generally moving in a direction that's parallel to my vector field, and so the circulation ought to be positive for this vector field along this curve. So here's a visualization of this vector field in the old vector field analyzer. And if I take a circle oriented at, centered at the origin, and I traverse this circle in a clockwise fashion, so by definition in this applet, in the vector field analyzer, everything is assumed to be counterclockwise orientation. So we'll just have to think, put a negative sign in front of every result that we see here if we want the circle to be clockwise. So when my circle is clockwise, this yellow area is going to be positive contribution to circulation, right? And so we're going to get a positive circulation for this circle around that, around the origin. If I make the circle bigger, I make the circle smaller, the answer is still the same. If I move the circle around, interestingly enough, I'm still getting the same value for circulation once again. So just like in our previous example with the rectangle, it seemed not to matter where we placed our closed curve. We end up getting the same value for circulation and the same ratio of that value to the area of my circle. That ratio in this case is -2. So that's another teaser for our Green's theorem result, which is going to relate circulation to derivatives of our vector field a little bit later on. So we expect the circulation in this first example to be positive because we're going around our curve in a direction that circulates in a consistent fashion with the way that the vector field circulates. We're moving parallel to our vector field along the way. So how about these other couple of examples where it's a little bit less clear, but it sort of reminds us of the example that we looked at just a few minutes ago. If we look at this vector field, let's say we take a look at this oriented curve, along the south side and the north side of this rectangle, we are going to be moving perpendicular to the vector field. And so those sides are going to make no contribution at all to the circulation, the path integral. Meanwhile, on the east side, we're moving in a direction that's parallel to the vector field. So we're going to have a positive contribution on the east side. And when I come around to the west side and I'm moving in a southerly fashion, we're also moving parallel to the vector field on that west side. And so that'll be a positive contribution as well. So as I go around this rectangle, starting in the bottom left, we're going to have 0 contribution, followed by positive, because we're going parallel to the vector field, 0 again, because we're perpendicular, and then positive again, because we're going parallel to the vector field. So if we put that in the old vector field analyzer, just to check our work, sure enough, we're seeing the positive contribution happening here on the east side, and then another positive contribution that happens to be even larger on the west side because the vector field arrows are longer over there. But on the south side and the north side, the contribution is 0 because we're moving in a direction that's perpendicular to the vector field. And once again, at least for this vector field example, it seems not to matter where in the xy plane that I place this rectangle, that the total circulation is the same. And in this case, it happens to be exactly equal to the area of this rectangle. There's that Green's theorem teaser again. And that same idea should persist if we choose this rectangle that's down here, except this rectangle is being parameterized in a clockwise orientation instead of counterclockwise. And so as I move around this rectangle, starting from, let's say, the southwest corner again, I'm going to start by going north, and that's going to give me a negative contribution because I'm going anti-parallel to the vector field. Then as I go along the north side up here, I'm perpendicular to the field, so there's zero contribution to circulation. And then as I go down the east side in a southerly fashion, I'm going to get a negative contribution because once again I'm anti-parallel to the vector field, and then I'm zero because I'm perpendicular to the vector field again. So negative, 0, negative, 0. And that's going to add up to a negative circulation around this curve. And so another way that you might think about this is, even though it doesn't look like this vector field has a rotational aspect to it, if I just sort of imagine placing a water wheel or something here at the origin, then all of this water that's flowing on the right half plane is going to tend to try to spin that water wheel to the counterclockwise direction. And all the water that's flowing on the left side is also going to contribute to that water wheel spinning in a counterclockwise direction. So it seems like if I were to place a water wheel at any point in this picture, that it would want to be rotated by this vector field counterclockwise. And so that means that my counterclockwise paths will give me a positive circulation, and my clockwise paths are going to give me a negative circulation. And that's the predictions we would make on this example.